push it back.
Yeah, that's a little close and personal. Do I want to make it so that Nina can do the controls? Yes, yes, I do.
Everyone has been doing a pretty good job.
You have been. Certainly doing a better job than I. Alright, so we're going to have a smaller class today, because I know at least Brad's going to be here. I think Mr. Drew may or may not be as well.
Wait, where's Brad gonna be?
Oh, Brad is on his way to Maryland.
Oh, the Baltimore meeting?
Baltimore, there you go.
Yeah, that was stuff.
Okay, so last time obviously we just followed that giant problem.
So,
Primed, yes, this is all primed. So the trick to this, and this is what I was regretting doing, and I think one of you guys actually kind of pointed this out to me, I just didn't want to believe it. Or I want to, is that if we separate this out into the individual setup, it makes it a lot easier. So then we've got the individual definitions in equations 220 on here. That we plug in here for UX, UI, and UZ, and then break it apart. You'll be able to solve out the entire term. You can then go up in the numerator. It does make it a whole lot easier.
So how many steps does this thing actually take you?
This part is the longer part. I don't know. It's a little over. It can be done on one page. I write gigantically, so it took me a page and a half. So, but I mean, when I solve, like any one of your example problems that we go through, take me at least a page just to write this. I mean, that's just a little bit. If you guys have problems with it, I will help you, David. It's not like I'm throwing you out there and saying good luck.
If you can find me.
If you can find me. You can find me during office hours.
Where's class or office hours?
That's a difficult part, yeah.
Which I think I'd have one for every single one of your office hours.
You know?
Yeah.
Well, then just send me an email and meet up a time. Or you can do what Jared did, schedule a meeting for the next day, and then just keep showing up all day long the day before. Anyway. So, that also works.
Oh, so you can be doing all right. You can be doing all right.
So, okay. Alright, so where did we leave off? Well, we left off with this bad boy, and then we tried to get to the idea that the momentum is conserved. Alright, so in the classical momentum equation, we had momentum before and momentum afterwards, and we just had the total mass times whatever the velocity difference between the two systems was. And we said, well, that's going to be conserved, because we're dealing with Newtonian reference frames such that the velocity is constant. Okay.
Prime on the end.
Yes. Well, yes. Sorry, hold on. No, it's not prime with an I.
Okay.
Wait a minute.
Prime.
Everything on this side can't be prime. Nothing on this side can be prime. This is how we're going to go back between the two. Alright, so this is your goal in your current homework for Tuesdays to get to this equation. Start here, get here. Alright, so this part right here, let's go through here and see what is a constant. Is this a constant? Is this a constant? Is this a constant? And is that a question mark? Or any of those question marks? They're all supposed to be question marks. Okay. Are they or why or why not?
Are they what?
Constants. Or do they change?
So the
Are they a product of what's going on in the reference frames, or are they constant? Go ahead, Jared.
So the velocities, V has to be constant because it's the difference between the two reference frames.
And that never changes.
Yeah.
So what about gamma V?
I feel like gamma V can change.
No.
No, because gamma V is just like gamma U here, except the V is here instead of C.
But I
So
guess
it's just a function of V and C, so it can't change either.
also quick. I figured out why I get no problem with using the cosine. Because that entire section I didn't use equal to was 1.
Yes, because you're supposed to use cosine of 0 or cosine of 180 degrees. So it'll either come out as 1 or negative 1. All right, so V gamma V is going to be a constant. This is going to be a constant. So if this goes up, we can say that this must go up with the exception of this quantity right here. Now, we're saying that if we sum the total momentum's initial times the mass initial, then we should end up with still a constant. Now, this is the weird part because this is just the initial mass. Okay? This is not what happens after the collisions or anything like that. So the conversion between momentum between these two is based on whatever we started off with velocities. It was kind of a weird thing. So this is where we're going someplace strange. All right, this stuff right here, when they were first trying to figure out what this is, Einstein postulated, let's call it an energy term. And literally just threw c squared onto the end. Just tagged it on. Said, look, that makes the units work out. Never mind the fact that c squared is a huge freaking number. There's a couple different ways that he came up with this, though, because simultaneously, there was two things that were going on. One, we had this momentum problem where we had this left over. We knew that this had to be constant, but we didn't know what it was. Okay, so he suggested it was possibly energy. Then the suggestion was, well, what about if it's kinetic energy? He wrote it in this way. Okay. Awesome. Thanks. But kinetic energy does not necessarily have to be conserved. Kinetic energy can be converted to potential energy, both of electric or gravitational, or any kind of potential energy you want. Usually electric potential when we're talking about this sort of thing. But it was total energy that had to be conserved. Now, we've always dealt with energy conservation in the standard 2211 or 2201, but not directly tied with the momentum. All right, so this, by definition, he was suggesting, which is the larger version of the equation. I mean, this isn't exactly E equals mc squared. We've got this larger thing here. This is the total energy of an object moving at speed u. Now, what do I mean by total energy? I mean total energy. Some concept that we're known rest energy we're going to talk about right now, moving energy, internals energy, any type of energy that you could possibly apply to an object is all in this one equation. And that's what we're saying, that this would be constant. So, if this necessarily down here is constant, okay, this gamma u mi, then tagging on c squared, c is definitely a constant, doesn't change anything. Then that it's obviously still going to be constant. Okay, so
we'll plug in c on the end of that equation.
what?
We all plug in c onto the end of that equation.
This is not, no, the c, this equation is without c, so this is the energy system divided by c. Okay. Now why is that? Where's the energy term come back in? You basically have your c term up here, multiplying by it up front. But here it's going to be c squared, so that we get units of energy as opposed to units of momentum. Yeah.
So I forgot, which question we were proving was incomplete?
What question we need?
No, can we just like last week that your source was incomplete? What was that? Is that the same equation or we on the...
This is, I think, I'm not entirely sure what you mean. This is the equation that we were talking about, we got to, that I talked about for the first 20 minutes, and then I said I wasn't sure how we got from here to here.
I'm talking about the lecture before that.
I don't know. What do you mean?
Yeah,
Something
yeah.
was sorry. Okay, so the idea of this is, it was really revolutionary at the point, and this is why the idea of E equals mc squared was such a big idea, that energy equals mass, and these two things are synonymous, that you can measure energy simply by taking the mass of something. Okay, so, now one of the things that is curious is, what happens when something slows down? We said that this is the total energy of an object moving at speed u. So let's take gamma u for a second, and look what happens as u goes to 0. What does gamma u become? Infinity, 0, or 1. Usually those are the three choices for anything when you take something to 0. 1. It just goes to 1, right? So as this goes down to 0, we have 0 term here, square root of 1 is 1, 1 over 1 is 1. Yay, really exciting. Now that's when we get to our classic equation that we have E equals mc squared. Okay, and this is known as rest energy. the energy of a particle which is not moving. Now again, this means all types of energies with one exception, kinetic energy of the actual full object moving. So if this has any sorts of internal energy, and we're talking down to the microscopic level, we're talking about quarks and the energy of the electrons within the system. This encompasses everything. All right, so then the question becomes, we now have an equation for total energy, right here. We have an equation for rest energy, so it should be easy enough to come up with an equation for just kinetic energy, a pure equation. So if we take this, we can say that our total energy, our TE minus RE, is going to be equal to KE, our kinetic energy equation. Kinetic energy being obviously the energy of the object moving. If that's the case, we've got gamma U mc squared minus mc squared. Okay, we can factor this out and say that's gamma U minus 1 times mc squared. Now, it certainly doesn't look like the kinetic energy that we've seen before. Not at all, in fact. Okay, so let's go through and push it around a little bit. Let's see what happens when we have a slow-moving object. Okay.
Kinetic energy is 1/2 mv squared by.
Yes, exactly. 1/2 mv squared. Alright, so now let's look at the total energy, or actually, yeah, we want total energy? Yes. Total energy for slow-moving object. So, an object that has a U that is much less than much less than speed of light. So, if that's the case, we've got our gamma U mc squared. Okay, so first thing we need to look at okay, this is getting close to 1, but not quite. We're saying slow, but not incredibly slow. So we're going to call upon the binomial expansion, which basically says, I can rewrite that equation right there as 1 minus u squared over c squared to the negative 1/2 c squared. I'm just going to keep going on this side. Okay.
What did you use for that?
I haven't used anything yet, sorry. I shouldn't even say that just yet. Haven't used anything yet. This is the exact same equation that we've got up here. Now, binomial expansion tells us this. I feel like there's 2 ones. No, I feel like there's 1. No idea.
I think it should be 1.
Okay, good. I can't spell. So
Oh, so you really know your word when you're walking the door?
say it.
Do you really note when you're door?
Yes, you're the one who called me a liar? Yeah, Jones actually enjoyed that at all. I forgot to take that off yesterday because I was there all day yesterday. Okay. Binomial expansion, which states that 1 minus x, or we do it like this, to some power n is going to be equal to 1 plus n times negative x. Okay, so for our case, we've got,
Did you say negative x?
yes, negative x. We've got negative 1/2 up here, where I'm going to let x be this u squared over c squared. So this is going to be equal to 1 plus a negative 1/2 times a negative x. So if we plug all of that in back over here, I can rewrite this now as 1 times plus 1/2 u squared over c squared times mc squared. Alright, you guys have binomial stuff written down? Why do you erase this? when I was going to grad school, we had these really cool whiteboards that, and I think they have them in some of the rooms here, that slide up and down. So they have 4 or 5 boards that you can just pull down and slide up. So, oh, it's so nice. So you write, but also the nice thing is, because I don't like writing basically below this. I mean, I'm not saying I'm that tall, but I'm trying to use this part of the board's obnoxious. So you can slide it up and just keep going and then put it up. So then when you start writing here, it's a perfect transition down. That was nice. All right, so let's multiply this out. Now here we're going to have, okay, so I'll have mc squared plus 1/2 u squared c squared mc squared. These cancel. mc squared plus 1/2 m u squared. So for slow moving objects, when we work this out, we find that we end up with this, which is our rest energy, which we're saying that every particle has, or any object has, and then we're saying that we have our kinetic energy, exactly what we would expect. And this is really where the math started to make sense. So this idea of throwing c squared in the end of this is, why are you doing that? It doesn't make any sense until you start to work through the math, and then you try it. Everything starts to make sense. This was the key that unlocked everything, that pushed everything together. And at least for me, eventually, when I was a student, this is what made sense for me. When you start looking at slow and you get back to the classical equation, like, aha, okay, I kind of start to believe you now. All right, so there's several different takes. If you look up on how Einstein came up with this, there's about 4 or 5 different angles. Because like I said, this was a key to a lot of different things that were all happening simultaneously in about 1905. So you can find 5 or 6 stories that will either take you the kinetic energy route, you can look at the energy loss rate from light, and this is the key to all of them. So you can show the same results of E equals mc squared of all of them. So we're going to see a slightly different one right now. Oh, to back it up, we're going to watch the relativity one, which I could have actually watched a while ago. These are pretty good. Yes, they are. Which one do we want? Okay, we're going to do this one, distance and special relativity. Okay, so we have a total of 3 of them that we're going to watch. I don't know if it's worth tuning this.
Just put a hyperlink to the video.
I will, but I mean, at least the camera's pointing at something interesting.
We should point it at me.
What? We have our heads.
Pointing at your heads.
What do we really mean by near and far? In a way, distance is just a measure of how hard it is to get between 2 points. The harder to get from here to there, the more distant there is. This makes
That's an
thinking about
important
distance in
idea to
multiple
think of it
dimensions
that way.
easier. In 2 spatial dimensions, a point a mile north and a mile east is more distant than one that's just a mile east. It's harder to get to. What about 1 space and 1 time dimension? Piece of cake. Getting to a point a mile east in a minute is a lot harder than getting there in a day. So 1 mile east and 1 minute in the future is way more distant than 1 mile east and a day in the future. And a point that's a mile east right now is impossible to get to. So it's super distant. But hold on, that would mean that a minute is farther away than an hour. Doesn't that seem backwards? It kind of is, but that's the way the universe works. In special relativity, more time equals less distance. So distance in time is negative. And if you travel east and into the future in such a way that the negative time and positive space distances cancel out, your total distance will be 0. And you'll be traveling at the speed of light. So how far away is tomorrow? It's closer than you think.
You don't have to think about that too much. It's probably the most confusing way to explain it.
For sure,
Yeah, the point with that is the only thing you really summarize that with is getting towards the idea that light moves such that it is everywhere at all times, at least from its point of view, which would be great to get light in that sense. There it is.
When the Galaxy Note launched in 2011, it was ahead of its time. And naturally, when things are new and different, sometimes people aren't ready for it. Experts saw the bigger screen and were like, you look like you're talking into a piece of toast. The Note is an unwieldy beast. Now it's not being dismissed by competitors, it's being imitated. Thing is, the note is more than big. It's about being more productive. Wait for it. I like that one. More innovative.
Just curious.
Oh, cool. More fun. Today people are saying, is it just me or does the new iPhone 6 look like a Samsung Galaxy Note 2 from 2012? It's cute how Apple thinks their phablet is a fresh idea when Samsung Mobile has been excelling at them for years already. Hashtag next big thing.
Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein with a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving.
It's just really neat with the way he does this sliding stuff. It's a
The
great
point is that the switcheroo changes relative things, like position and velocity, and not absolute ones, like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick, and it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
Okay, so I want to go back and talk about this side. So this is more important than he led on to, just for you guys to see.
We were assuming that our switcheroo had to
what?
every slice of time at the same time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time
Okay, so
while sliding them, then we can keep.
So what he's talking about is in the same axis. You're still looking like this as to the distance it is close to this person. So when we look at this now, okay, so we see this right here, and then we see the sliding. So from the point of view of this cat, okay, we're seeing these as simultaneously. They both happen. Time is on this axis, like this, happening, okay? So from his point of view, these both happen at the same time as time is going like this. From this person's point of view, from the slant, since they're moving, this happened in the past, the bottom one, because that's lower in time, the other one happened in the future. So it's a pictographic way, I don't know if I really want to use that word, but to show that. So from this person's point of view, this one happened, then this one happened. This one happened, then this one happened, this one happened, and this one happened. Even though that they're
Then we can
still
keep
the same distance, it's still
and
traveling
things can move
at the
too.
same rate
Of course,
away from
Einstein
You're
didn't
just
figure out
saying
this special principle of relativity in
relativity.
1905. It was already done by a guy named Lorentz 10 years earlier.
Now,
But
the very complicated version of this is in the back of your book. It's one of your appendices. It is appendix. Let's take a look. I think it's appendix B.
I'm just confused, or I just can't think today.
No, that's all right. Appendix B, Lorentz transformation plotting events. This is what Lorentz came up with. Okay, this was a neat mathematical trick that then fit all the puzzle pieces. Again, nobody took it too seriously. Not that anybody took Einstein all that seriously when he first came up with it either. But okay, so now we want to move on to E equals mc squared. Where this came from?
We're supposed to understand this appendix B.
No, don't worry. You're not responsible for it. I think everything we've done, hopefully you can grasp onto the stuff we've done. Okay, good. Appendix B is difficult. It is very difficult to understand how it goes about that. You are not responsible for it.
Is it appendix B?
To be able to buy its full color head-up display,
keeps you focused on the road ahead.
This doesn't look really super car.
Even when you're driving the BMW 3 Series. It's another BMW i8 innovations available. BMW 3 Series. We only make another third. The ultimate driver.
In mid-1905, Albert Einstein derived what is now the most famous equation in the world, E equals mc squared. But he didn't just write this down out of the blue. He followed directly from his paper on special relativity that we talked about in last week's video. And here's how he did it. Suppose you're watching a cat float freely in empty space, when suddenly it emits a flash of light in all directions. The light carries away some energy. We'll call it E. So by conservation of energy, the cat must have lost energy. But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy for the light come?
Okay, so since it doesn't go
From special
slower,
relativity that we talked about in last week's video.
I'm going to pause.
Here's how he did it. Suppose you're watching a cat float freely in empty space, when suddenly it emits a flash of light in all directions. The light carries away some energy. We'll call it E. So by conservation of energy, the cat must have lost energy.
Okay, so he emitted some light. Light has energy. Now we're starting with that. So if he's done this, the cat has now less energy. That's all he's saying goes so far.
But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy for the light come from? Never mind that now.
Well, that's an important idea. So as you're moving, you can emit light. Light has momentum, but it has no mass. So we're saying as the light goes away from him, it didn't change the velocity, so the energy had to come from where? Gotcha. What?
Light?
Yeah.
The light has
Or
no
something
mass,
like
which means
light,
it
the light
should have no
is-
energy or
Yeah.
It's the equation, right?
Well, what light is, now that's the weird thing.
Because it's a particle and a wave at the same time.
Yeah, light itself doesn't have energy. Light itself doesn't have mass. It is pure energy. So it goes away, it has energy. So where did the energy come from in terms of the cat, if it did change its velocity? It's mass. Okay, but let's just go with internal energy right now. We can just classify it as internal energy. So if the light went away from the cat, the only way that that's going to happen is if the cat got lighter.
Let's imagine you get bored and zoom off in a spaceship in the middle of the experiment. But from your new perspective, you're sitting still in your spaceship, and the cat is the one moving past outside the window. Therefore, you'll calculate that the cat has some kinetic energy, that is, energy of motion. And when you see the cat emit the flash of light, you'll again measure that its energy decreases by the end.
No, this happens up in my office too. I actually did a speed test on the internet for Shawnee today, and I got a download speed of about 2 megabytes per second, which is terrible, and an upload speed of 70. I couldn't believe how fast the upload speed was, but that's not what I need.
Light, you'll again measure that its energy decreases by the energy of the light. Except now that you're moving, special relativity tells us that time passes at different rates for you and the cat. So you'll measure a different value for the frequency, and thus energy, of the light. This is the relativistic Doppler effect.
So we already
For
talked
our
about that.
purposes, it amounts to multiplying the energy of the light by 1 plus your velocity squared divided by twice the speed of light squared.
That's
So to
what we
recap,
get.
if you take off at velocity v, you'll see the cat gain some kinetic energy kv1. Then at the flash, you'll see the cat's energy decrease by v times 1 plus v squared over 2c squared. On the other hand, if you wait, you'll see the cat's energy decrease by e. And now when you take off, you'll see it gain kinetic energy kv2.
Okay, so these are the two scenarios, saying that you stay and watch the experiment, and you're just watching the cat flash, so the cat must lose a negative E. And then you take off. Okay, now you're going to look at the cat having some kinetic energy. I suppose if you take off, in the first place you can say the cat has some kinetic energy, then the flash, and so this is going to be the change in the flash. The energy level you're going to see is different because you're moving away, Doppler shift.
But this is silly. You never touch or otherwise influence the cat in either case, so we should get the same total energy at the end. Rearranging, we see that the kinetic energies before and after the flash must be different. And the kinetic energy of an object is 1/2 of its mass times its velocity squared. But we know that the velocity was the same in both cases. So in order to account for the difference, the cat's mass must change when it emits the flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must be equal to the energy of the light emitted divided by c squared. Or, as you heard before, E equals mc squared.
It's another way to look at it. They're trying to figure out how on earth the cat could emit energy. I don't think that was Schrodinger's deal. I don't think that was Einstein's per se. I don't know that he was that obsessed with cats.
In mid-1905,
No,
Albert
it's-
Einstein...
Is that ASAP science? Like saying you can do that?
I don't know what you mean.
No.
Hey, look, kind of saw the corner of the video.
I feel like the scientists are more cat-people than dog people.
Hey, I don't know about that, but I'm a dog person. That the vet this
Maybe
morning
they
is
use
9
cats
o'clock.
because you don't want to hurt dogs. So.
Yeah.
Yeah, there you go. No, at the vet for a freaking half hour, they give you an appointment. I understand the whole people thing over there forever, but just the same with the dog, sitting in the waiting room for a half hour. My dog begging me, can I go play with that dog? Can I go play with that dog? Can I go sniff that crotch? No, you can't. Sit. Stay. Okay, so how can we use this? All right, well, first place we're going to use this is inelastic collisions. Now, in undergrad, we talk about inelastic collisions. We say, you've got an object headed this way, object headed this way. Bam, they collide into each other and go squish. Okay, and we solved that using momentum transfer. Now, if both objects have the same mass and are moving at the same velocity towards each other, what's the momentum afterwards?
Same.
Well,
Go in opposite direction.
no, inelastic. What's the difference between inelastic and elastic collisions?
Oh, okay, they stick.
They shake. Yeah, inelastic is when stuff smashes together and stays.
Oh.
So for inelastic collisions, what is the momentum afterwards if they have the same mass and same velocity coming in?
Zero.
Zero. Yeah, they go boom and they stick together. Okay, now what was the momentum beforehand? The total momentum.
Oh, would it be 2 times?
No,
We've seen.
it can't be. Conservation of momentum.
Zero.
Why?
Because if you're looking at the system, I mean, the momentum of the first cancels the momentum of the second.
Why? How is that possible? They both have momentum, they're both moving. So how do they cancel each other? What's the key here?
That the momentum of one is equal to negative the momentum of the other.
How can momentum be negative?
Because of directionality, it's a vector.
Vector.
Is that relative?
Now we're getting there. So momentum is a vector quantity. It has direction. So if it's going one way, it can be positive. If it's going the other way, it might be negative. So when we originally had this, we can say that this one plus this one, we can set a positive direction. I really don't give a damn which way it is. One of them is going to be positive, the other one's negative. As they collide, we now end up with zero momentum here, which means we must have zero momentum there. All right, that's just a refresher from before. Now, the one question we didn't ask is, what about energy beforehand? There was definitely some energy beforehand. Energy, is that scalar or vector? It is a scalar, yes. Energy is just a pure scalar. It does not have direction. So afterwards, when we got energy final, then where the heck did this energy go? So that's our first question. Where did the energy go? All right, so we have this loss of kinetic energy very specifically. So if we write this down, we can say our initial situation, let's look at just one of the objects. Okay, let's look at object 1 right here. The other one's obviously going to be the exact same in the other direction. Since this is a scalar, it doesn't matter which one we go. So object 1, initially, with our new equation, we're going to say m1 is going to have some sort of rest mass times c squared plus 1/2 mass ui squared. Again, we're talking at slow speeds, so we're ending with the equation that we just saw for slow speeds. And it's going to equal our m final times c squared. Whatever the mass final is c squared. This would be another way that we can figure out that the internal energy is necessarily going to change. All right, so what's going to go away here? Now, we can just represent this as KE, and if I bring this over to the other side, I can say I'm going to have mass final times mass initial times c squared. And so in this way, you can kind of see this, that this is E equals mc squared, but we're saying that the kinetic energy is equal to the change in mass that we're going to see times c squared. And it's true for a small object. All right, now, how large are these changes of energy? Okay, mass equals energy. Lovely. We may or may not believe that, but we're going to go with it for the moment. All right, so now the book makes an interesting point of saying that if you have the mass of 1 kilogram, a 1 kilogram mass, and you turn that into pure energy using E equals mc squared, it's enough energy to launch the Empire State Building into low Earth orbit. It's a huge amount of energy.
Wait, what?
If you have a 1 kilogram mass equals mc squared, so use 1 kilogram, just a 1 little kilogram mass, and you convert that to pure energy, it's enough energy to put the Empire State Building into low Earth orbit.
I've heard like similar like a giant bomb, right?
That would be a giant bomb if that happened, yes. And today in news, the Empire State Building is in lower orbit. Yeah, that'd be a big bomb. But this mass versus energy thing, also changes your approach to cooking recipes. Instead of saying, bake the lasagna until it's 325 degrees, bake the lasagna until its mass is increased by 0.1%. Then you're done. You could say that, because that is true. You've added internal energy to anything you've cooked, anything that you've heated up, so its mass will actually increase. But by how much? Okay.
So you use this to your advantage when you're buying stuff.
Sure. How? What, you're going to deep freeze everything so it's slightly lighter and then get your produce? Okay. That's what I was trying to tell. So in my 2201 course, we're talking about apparent weight. So I'm teaching the students the idea that on the moon, things weigh less. So also, when large celestial objects are near Earth, they affect our gravity. How do we know that? What's a good example of that?
Moving?
Yes, which affects what?
Tides?
Tides, yes. So when the moon is closest, we have high tide because it's actually pulling the water towards the moon. So I told them, anytime you want to go buy produce, go buy it on high tide because your bananas will be cheaper. Which is true. Obviously, probably not as much as the skill to be able to read.
Hey.
So now, you guys know. Now you're at the next level of physics. Physics is just about figuring out how to get your groceries as cheap as possible. So now if you deep freeze your bananas, you've removed some of their energy, so you actually take away some of their mass, and you've got to buy them at high tide.
So you use
Well,
this
no, because then the water around the bananas will condense and the bananas will freeze, which
Yeah, so that's
But you should also do this near the speed of light, so that way your shopping trip takes, considerably less time.
You've done 5 minutes before anybody else sees you.
I don't know if there's a money contraction formula. I'm not sure about that though.
Well, it might not, well, I mean, time is money, so if you
You
take
already,
less time.
you already
will
checked
save
out
money.
and get cashier your money before the cash register realized you haven't got money.
Have you guys seen that thing where it talks about why I don't date and started off with saying girls equals this and time equals money's in there and somehow it ends up with girls equal evil?
Yeah, I've seen
I
that.
forget how that worked out, but I thought it was pretty entertaining. Alright, so mass equals energy.
It's because, I think it was like, money is the root of
Girls,
evil.
money is the root, yeah, and then so the square root of evil, I forget how all that worked out, but it was kind of entertaining. Alright, so 2 scenarios we want to talk about. First, we've got hydrogen here.
Yay, hydrogen atom.
Yay! So we got a proton and an electron running around. And these guys are going to smack into each other. So we got a nice little Venn diagram. We got 2 electrons running around each other. Okay. So, in doing so, now we've created a new molecule. Yay! Now, is the energy of the system higher or lower than it was before?
Isn't it the same?
It's actually
I
lower.
mean, the system gets less chaotic, so I think it's something.
Yes, well, you've actually lowered the electrical potential energy of the system. Yeah. Say again? Yes, it's more stable. Exactly. It's a more stable system. And anytime you have a more stable system, you are, by definition, decreasing its energy. Okay, so if that's the case, we're decreasing the electrical potential energy. Yeah. This is
And
In
you
fact, we are specifically talking about the difference between chemists and physicists right now. Let's see
I
why.
actually told me that if I go back freshman year, I would have been physics major.
Who said that?
I said that to her.
That's awesome.
yeah, I tried to,
If I
and
could
then
go
I
back in
got
time,
a
I
physics
would have
degree.
changed it.
You want to change it?
Yeah, I would.
Nah, that's good. I like to hear that.
See, Dr. Ross, I did also though, because I found out we don't have a physics degree.
Well, we're working on the physics degree. I'm working on the physics degree.
Oh,
Actually, no, that isn't true. Hamilton's working very hard on the physics degree. I need to get him to teach an optics course. Is the thing. I want to get him to do that.
Yeah.
All right, so we have a decrease in the electric potential energy. How much? When this happens, there's energy that's released 7 times 10 to the minus 19 joules. Now we're just talking 2 atoms creating 1 molecule, so it's not like a ton of energy. How is this energy released instead?
What?
No, I
Electric
have a
potential
variety of
change?
ways, but photon is one of the ways. So you can release photon, which say that you release light. Okay?
Electric potential change?
Yeah, it's electrical potential between the 2. So it's a loss of the system's energy. Okay, now we're finding electrostatic forces here, so that's what's actually been reduced. Okay, so now when we use E equals mc squared,
So is it E that's equal to 7 times?
E is equal to 7 times 10 to the 5. Yes. Every time I do this, I'm just taking the energy of something and saying that we can put it into this formula, and we can always calculate the mass. So what is the mass associated with this transition? The mass is going to be 8 times 10 to the minus 36 kilograms. All right, so not a huge amount. What's the mass of an electron?
Like 1.17 times 10 to the negative 30.
No, it's 9.1.
You said, like 1.17 times 10 to the negative 36.
Close. What was the last thing you said? What was the exponent?
10.
The negative 31.
31. Okay, I think you said 20 first.
Wait, was there negative? Was there
Negative
negative
19?
Okay, now you guys are mixing. We
This
need to
physics,
know all of
not
this stuff. It's
chemistry.
going to matter
I
today.
think you should.
So, for specifically, so Brad doesn't get to know. Mass of the electron is 911 times 10 to the minus 31 kilograms. These are really useful things to know. All right, mass of the proton.
1.1 times 10 to the negative 19.
No,
Am I close?
27. 27 for starters, so no. But it does start with a 1.
1.67?
There we go. You have to look it up, or you just...
It sounds like a good number.
No, right. All these numbers can mix up if you don't use them for a while. I end up using them a lot. All right, so then
It's the same, right?
E, what is the elementary charge? That's the other number that you guys are starting to spout. That's what you keep saying over there.
The 1.1.
No. There's no 1.1 ever that I know of.
The 1.
There you go. Say that.
Times 10 to the negative 19.
You didn't say the full words. 1 point what?
1.
No! 1.6. 1.609. So 1.61. You can get away with that. 1.6 times 10 to the minus 19 coulombs.
Okay, so there was a 19 somewhere.
There's what?
There was a negative 19 somewhere.
The 19 you had right, yes, but you were stuck in this 1.1 bit.
Is there 1 point something we use the biggest?
Not that I know of. Not that comes to mind anyways.
You should go
What's like the mass
develop
of
something that uses 1.1.
Yeah, maybe.
No, the mass of the Earth wants to start. Radius of the Earth is 6,400 kilometers. The mass of the Earth, I forget.
Really, yeah.
Doesn't start with one. Big, yeah, large.
How did they measure the mass of the Earth?
You know, as you said that, I was thinking that myself. I
It's
don't
not in the front.
They're using a very big scale.
Who's the god that's apparently supposed to be holding it up? Was it Atlas or something?
Yeah.
They ask him. How heavy is this?
Yeah.
Wait,
Again,
did they just
Atlas shrugged.
Wait, did they just Did they just calculate the gravitational effect? They just calculate the gravitational effect of nearby objects, like the way it is warping space or whatever?
That's one of the easiest ways to do it, right? You got the moon going around at a certain rate, and you've got the Earth going around the sun. But no, here's the thing. To answer that, you have to make assumptions about the mass of the moon and the mass of the sun to be able to calculate the mass of the Earth. So it's, you know,
If
chicken
I
and
can-
the egg
do-
issue.
All other planets around it.
But you have to know those masses too.
Okay, so they shoot a rocket
So
up,
it's
it's
a
a
real
kind of rocket that they know the mass of.
We knew the mass of the Earth before.
Well, here's the thing. Okay, so
Don't know.
you guys like distracting me. All right, so Newton's law of gravity. What is Newton's law of gravity? It's got a big old G in it.
Yeah, big G, then it's like little g1 plus little g2 over g2.
Isn't it?
Looks
N?
like
Geez, you want in this equation?
What
No,
you said, the
that's-
M?
Well, so far we've got a
Yeah.
capital A.
Is there
Mass
a
1,
degree?
mass 2 over r squared.
Okay.
Now, if you remember, when you're dealing with Earth, we put Earth in here for mass 1, mass 2. This quantity right here is equal to 9.81 meters per second squared. So, assuming that, heck if I know how, if we could somehow know the gravitational constant, it's pretty easy to figure out the radius of the Earth. That you can do just using light and figure out the rotation period and when light starts. You can actually make some good calculations of the radius of the Earth. Hamilton obviously is the one to be asking this. But from that, you could backwards try and calculate what the mass of the Earth is.
And
What do you got?
what if you measure the gravitational effect, and then you shut a rocket off, and then measure the difference?
Then I sign it for you as a homework problem. I can actually scratch out your homework problem, Dave, and I'll give that to you specifically.
This
Okay,
is for him, not me.
so, what'd you say?
So this is for him, not me.
There you go. All right, this mass is smaller than the electron mass. It's obviously smaller than one of the proton masses. So we can say that this is 1 billionth. Do you add the E at the end? That just looks, no.
Using the
that right then?
Sure.
Sure. Okay, change it to U.
Yeah, put a U in there.
1 billion. 1 billionth of a nuclear mass, of molar mass.
Yeah, there's no E.
Okay, of a nuclear mass of the 1 proton. Okay, now, there's another way we can do this, using the exact same or the relatively same mass. Can you rotate me here?
No.
Brad's gonna hear you say no.
I like how you notice that you don't control it, but you need to move it.
Yeah.
When you were in charge of controlling it, you forgot most of the time.
Yeah, that's true, I did. It is interesting. It does help to have that background again. Okay. Peony. Same thing. Now we're going to, instead of slightly peony, I'm going to change this ever so much. Ta-da! Right. This might look like it's drastically different, but it isn't. Now I've got a neutron coming and hitting a proton. All right. Now, what is the mass ratio difference between an electron and a proton?
A lot.
Yeah, it's over 100,000. Big. Okay, really big. No, actually, that would be, it's 250,000 is the mass ratio specifically for xenon, so it won't be quite 100,000. Something less than that. Yeah, go ahead and give me a number.
Like a little more than 1,800.
1,900? That's it?
Closer to 1,800.
Interesting. Okay. Now, next question for you then. Which is bigger, or the same, neutron or a proton?
Oh, they're the same mass.
They're roughly the same.
They are roughly the same. In fact, if you want to flip to the front of your book, you'll see it on the cover. The mass of a neutron is slightly heavier than the mass of a proton. Ever so slightly heavier.
But they don't change what you wrote down.
What do you mean?
With the mass of them. If you're just doing 3 significant
Ah, you're only doing 3 significant figures. It doesn't, right? So let's say you're doing it out to 8 significant figures. This scenario, I just want to point out that this is pretty much the identical scenario as to what we're dealing with here. So, the mass of the neutron is actually larger than the proton, more than by a factor of an electron. So, even the fact that we don't have the extra electron here when we're combining these two, this system is 0.006% heavier. A very small number. So we can treat these as far as mass goes, nearly identical systems. But now, instead of the chemical reaction that we're having here, combining these two in a molecule, now we're going to have a nuclear reaction. This is why physics is cool. So what we're going to take with this neutron is say, hi, I'm going to force you into the nucleus. So I'm going to shove this down the throat of the nucleus such that we now have
What a nuclear reaction is.
So, yeah, I'm not even going to make that joke continue.
Okay. Tell me later. Okay, now that we've got this in here, all right, this process is a nuclear process, okay? We've actually bombarded the nucleus with a neutron and we've made it heavier. What is this now?
An element. An atom.
Well, I'll give you a hint. There's a specific name for it.
Ion.
It's tritium.
Close. It's the other one. Heavy hydrogen. What do you got?
Deuterium.
Deuterium. So this is a very important part of all nuclear fission processes. Fusion processes. Okay, so we smash these together. Now this releases a bunch of energy. The amount of energy this releases is 4 times 10 to the minus 13 joules. All right, still, minus 13, so it's not that big of a number. But if you do this in terms of the nuclear mass, you get 1/1000th of a nuclear mass. I'm just writing that as NM for the moment. All right, so the same 2 products to begin with, relatively, we've got a neutron and a proton electron, or the proton electron over there, combined in 2 different ways, and this one we're getting 1/1000th of the mass, and here we're getting 1/1 billionth of the mass. So we're getting a huge release of energy, which is one of the reasons that fusion is so awesome. All right, so pound for pound, nuclear beats chemical reactions, and the book actually says that. I love that.
And you know what? Nuclear is still chemistry.
No, blah, it's not. All right, so let's talk about a balloon for a little bit. we're just going to talk about some of the stuff that's in the book, and if you want to read more about it, you're welcome to. You have the book. All right, let's say we've got a helium balloon. We fill it up with helium, and then we heat up the balloon. Now, if we heat up the balloon, what can we say about the mass of the balloon?
It gets heavier.
Yeah, we've actually increased the mass of the balloon. Now,
It
here's
has to do with
the
entropy.
weird part.
It's gonna float easier now.
No.
It's going to
Because entropy
You've
also went up.
You increase the mass, but you
Yeah,
increase the
it is. So
density.
you increase the entropy. No, these are not. Entropy's on more of a macroscopic level than, I shouldn't say macroscopic level. Oh, I want to phrase that. On more of a measurable level? No, to my knowledge, this has nothing to do with entropy, unless I'm missing something mentally right now.
Well, entropy is like the how chaotic system all it is.
Yes, the idea that things don't want to go back to being in order, they continue to become in disorder. The whole idea that the universe just wants to spill out and be a big pile of goo of all about forces, and then not move. Which really doesn't make a whole lot of sense, though, when you talk about how are we here, then? Because we seem to be getting more complex, not less complex. Organisms are getting constantly more and more complex. So there's an interesting biological argument that's on the opposite side of that. Anyway, you can ask the universe about that one. So, massive balloon gains energy. Now, what about the individual molecules within the balloon? What happens to them when you heat up a balloon?
They speed up.
They speed up. They increase in kinetic energy. The individual molecules are running around. They have more kinetic energy now as they bounce off the insides of the balloon. Do they increase in mass?
They have
I guess they would have to because they gain more energy.
One would think, but no, they don't. There's no reason. Whatever you think the answer is, it's the opposite.
Yeah, but actually one
They
day-
don't. There's no reason that they would increase in mass necessarily because all they've done,
because they're increasing in energy, so that mass themselves.
they are increasing in energy, which is kinetic energy. So they're moving faster. They're moving faster, but their mass is not increased. Now, the way to think about this is, if I had that same balloon, now I'm talking macroscopic, I had the balloon, and I threw the balloon, does the mass of the balloon increase?
No.
I just want to see what Jared thinks.
Stay the same, I guess.
No, it doesn't. Yes, so you got it right. Well done. I know the mass does not increase, it does stay the same. Sorry, in case I was confusing. So if you throw something, you're increasing its kinetic energy. You're not increasing its mass. So if you're heating something up, you are increasing its mass. So if you were to heat something up, yes, the mass has gotten heavier. If you cool something down, it has decreased. So inside a balloon, now here's the weird thing that isn't really answered. If you heat up a balloon, the balloon is heavier. Fact, as far as we know. As far as we can measure this now, we can do this. The individual constituents inside the balloon do not get more massive, they just move around.
So where does the mass go?
Where's the mass? Yeah, you guys can we watch How I Met Your Mother?
Yeah.
Where's the poop? Let's think of that. I don't know if you remember back then, that was Lily's. Where's the poop? Where's the mass? And the thing is, mass doesn't have to be conserved. The large outside object can have a certain amount of mass, even though if you add up the individual constituents inside it, you won't get the whole mass. There's a difference. And the difference is the energy of the constituents on the inside of it. Yes?
Well, if you heat it up the balloon, wouldn't it cause it to expand, meaning that there's a bigger area of gravity to affect on it, making it heavier?
No.
Okay.
Gravity effect.
Let's just throw that out there.
Oh, okay, so now we're getting into really complicated things, and the reason being is, I can give you the simple answer, but why do that? The simple answer is to say that gravity affects mass, and although you've increased it, as it heats up, the mass hasn't changed. What we're saying that the mass does microscopically change.
But you decrease the density.
But you decrease the density, not increase by heating it up, because the kinetic energy is going to force these things to bounce back and forth, so that all they're doing is pushing on the outside of the balloon, causing more pressure. We're having fun, Jared. This is what fun feels like. Okay, yes?
I think this makes sense, so I think I'm wrong.
This is making sense to you, you're saying?
Yeah, so I think I'm understanding something.
No, this is
Yeah,
good.
say again what you said about
That or my
The mass of the
when
balloon.
you throw a balloon and then when you heat up the balloon, like how that.
If you heat up the balloon, the balloon's mass is going to increase.
Okay.
Okay. Now, because you can add energy to the internal constituents to it. Now, the internal constituents themselves, the molecules, will not have had mass increased in them. They just have increase in kinetic energy. That conversion to energy takes place when you mass the balloon. So you say, I'm massing, I want to know the mass of the balloon, and I'm just taking the mass of the balloon. If I counted all the molecules in them and add their mass up, I would see that it's less than the mass of the balloon. Because when you're massing the balloon, you're also measuring the inside energy of the balloon as well. And that's the weird thing. Mass does not have to be conserved, which is a really, you understand, so you don't want to hear anymore? Is that what's going on?
What?
You understand, so you don't want to hear anymore?
I'm afraid that you're confused me.
No, I totally understand that. I've had students tell me that before. They're like, I understood, and then you kept talking.
And it's happened before here.
I have a feeling that happened a lot in my physics class.
Yeah. So, okay, mass doesn't have to be conserved. Energy does have to be conserved. So if you added up the internal energy of all those particles, we say that we heated up the balloon, so we added energy to it. That energy went into the kinetic energy of the particles. So if we add the rest energy of those particles plus the kinetic energy of the particles, that will total the total energy of the balloon. The mass, however, is going to be different. Okay. Now, this only works for particles that have internal constituents. What? Okay, there's something called fundamental particles. Okay, fundamental particles mean that there's nothing smaller than that.
Like quarks and all that?
There you go. So the question is a proton a fundamental particle? No.
It
Is a neutron a fundamental particle?
No.
So both of those masses can change.
Is electron?
Electron is.
Okay.
An electron.
Wait, it's for but it's for
Electron is a fundamental particle. So since an electron is a fundamental particle, it has a fixed mass, or what is known as an intrinsic mass. Okay? So I spent, an entire semester in 2201, 2211 teaching people that mass is an intrinsic property in things, and it isn't unless you're a fundamental particle. So now I'm spending all this telling you, everything you learned is wrong. We should start this whole class with everything you learned is wrong.
That's pretty much what I've told
You should
people.
just-
Like people from 2201. It's like, yeah, get the modern. Everything you learned is a lie.
It is, yes.
That's not what I'm speaking. That's not what I'm speaking. Everything I learned organic was a lie.
Just start this
Okay, well,
class
I'm not
every day.
getting
with
it. I'm gonna
something
read
your
it.
house on. Everything you know is wrong. Just every day. You play that and you say, welcome to modern physics.
So, the question becomes, if you have a fundamental particle that, as far as we know, has no internals, it is just what it is. It is infinitely small. There's nothing made of it. An electron is a fundamental particle, and you talk about quarks and things like that. How do you add energy to it?
You speak
There is
carefully.
only one way, the kinetic energy. That is the only way you can change a particle, a fundamental particle's energy, is by speeding it up.
Or I got
You
another answer.
cannot change its mass. See?
I got another answer.
Okay.
I went to the next class, you tell me something else, you told me to lie.
Yeah, I can do that. It'll be good times. All right, so onward. Okay, let's go through example 2.9. Yeah, and quickly. What's working?
What?
Oh, one thing I do feel good about. I was interested about this because I kind of feel like we're not moving as quickly as I wanted to. So I went and looked at some online syllabi of other courses. Chapter 2 usually takes about a month and a half to go through. So I'm like, oh, all right, so we're not doing too badly. And it looks like other people kind of do the same thing with it.
So we should definitely slow down.
We're doing okay. We're 36 pages into a book that we're 5 weeks into the course.
But we have to do
Yeah.
a chapter.
So
This is the 5th week. This is the end of the 5th week.
We know we also class period last week.
I say yes, but from my point of view, I'm not looking forward to winter right now. I got my motorcycle back yesterday. I just got, it was so cold. Yesterday, of course. Yesterday was what, like 80 something during the day? Got down to, I think, 49. I'm sure it was wonderful. Freezing.
I just got a Jeep, so I'm good to go.
See there? Oh, did you really? Oh, that's awesome. Manual?
No.
That was a really good question.
I don't think because I've driven it once since I got it.
Oh, okay.
Oh, Chris trucks me a lot of them.
2.9. Okay, example 2.9. Let's get through this. The kinetic energy of a proton is half of its total energy. A, what is its speed? Okay, so we've got the kinetic energy of P equals 1/2 its, is it rest energy or total energy?
The internal, I think, is rest.
Is it say internal energy? Okay, so rest. I thought I wrote it down wrong. This doesn't make any sense. This is not solvable the way I had it. All right, so part A says, if that's true, what is the speed of the particle? So let's practice using this stuff. Speed, all right, kinetic energy equals 1/2 this. So I can say that my kinetic energy is going to be gamma u minus 1 times mc squared is going to be 1/2 mc squared, my rest energy. All right, the mc's go away. We end up with gamma u minus 1 equals 1/2. Or if we put it over to the other side, we can say that, why do I keep doing that? Gamma u is equal to 3/2, or 1.5. Now, the very quick way to solve for speed when you do this stuff, always use my substitution as x as that quantity u over c, or v over c, and it speeds everything up. So now I can say that I've got 1 minus x squared minus 1/2 is equal to 1.5. So 1 minus x squared is equal to, what exponent would I put 1.5 in on this side to get rid of this over here? It's calculator stuff. What do I want to get rid of this exponent. I've done it on this side. What do I put on this side?
-2.
-2. -2 times -1/2 gets you +1. So I say to the -2, which gets me an answer, I do believe, of 0.44. Now, the one thing you got to be careful of is when you do make the substitution, do it as x squared, because this is not the solution. I have to do 1 minus this. So x squared is equal to 0.5555, blah, 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 blah. X, therefore, is equal to 0.745c. All right, that is our speed. So that's an example way to do this. You've got a very, very easy homework assignment, which I'm going to hand out in a minute, that gets you to practice using these. So that's how you bitch so much about the derivation. All right, B. What is the total energy of this thing? Probably have to rotate this. Total energy. Gamma u mc squared. So this is just a plug and chug. Now we know gamma u is 1.5 times the mass of this, which is 1.67 times 10 minus 27 kilograms. 3 times 10 to the 8 meters per second squared. Put all of that junk into the calculator, we get back an answer of 2.25 times 10 to minus 10 joules. Now again, we're dealing with these super tiny numbers that are kind of hard to conceptualize, so it's easier to convert to an electron volt. How do you convert from a joule to an electron volt?
What is a joule again?
Oh,
I forgot.
Joule is a Newton meter. So it's a kilogram meters per second squared times a meter. Joule is the measurement of energy.
All I know is
So when we have the joule, another way to think of it is a joule is the amount of energy that it takes to raise 1 milliliter of water 1 degree Celsius.
You should think about 2.25, right?
Huh?
You think about 2.25 once you convert it.
No, I don't know what we're talking about. Okay, sorry. How do we convert from joules to electron volts?
I used to know this.
Yeah, there's something on the other board that helps us.
Like Google.
Oh, that's the energy thing. 1.6 thing.
Yeah, you're times 10 to the minus 19. So we can use the, we say electron volts, the amount of energy it takes 1 electron to go 1 volt. So we have to use the charge of the electron. So all you have to do is divide by that number, and we can figure that out. And the answer becomes 1409 mega electron volts, which is a good amount of energy for a proton. Not a huge amount, because if you're, it's not an electron, but as a proton, it's a pretty good amount of energy. Next, the potential difference. Okay, we got, yeah, we're doing okay. I'll come back over here.
Right, quite far there.
What do you say?
Right, quite far there.
4. Well, I didn't want to leave you guys without at least running through an example in class. As it is, your homework says read the next two, see? All right. D, potential difference.
D?
C. I don't know, pick a letter.
There is no D.
Oh. But there is F through H, David, so get used to it. All right, potential difference. Now, wow, look how this just kind of failed as I turned around. There's, yeah, difference. All right. Potential difference. What it's asking is what electrical potential would we have to have this proton fall through for it to get up to this level of energy? All right, now we got to reach back to 2212, which you all had, but one of you with me. Okay, 2212. How do I figure out the potential difference? Now, when I say potential, what kind of potential am I talking about? Stop trying on each other.
I didn't mean to, like his hand ripped.
All right, what is the electric potential is the answer is looking for. Okay. All right, what's the equation for electric potential?
That was too long ago.
Anyone? Any guesses?
I know, what is the book, Michael said?
That was not too long ago. She's kind of got it in the past. That was 2 years ago. Wait, Jared, were you in her class? Were you last? Yeah, you guys were 2 years ago too.
So,
Yeah, because you're looking at the book. Look at that.
well, hey, I didn't take class, so.
You know, he has
Delta
a pretty
V
fair defense.
times Q. Yeah, fine. All right. So, what is our goal here? Now, you guys are going to probably recognize this. Now, what we're going to say is we're going to say the kinetic energy initial plus the electric potential energy initial plus kinetic energy final plus the electric potential energy final. Yay, our nice energy conservation formula. We can still use this. The whole idea being is that we start off with zero kinetic energy. What sort of electric potential energy do we need to get to so we have this much final kinetic energy? So we can say that our kinetic final energy is just going to be equal to whatever this is, which is delta V times Q. All right, so for this amount of energy, what is our formula for the kinetic energy? Formula for
Give it -1 times.
There you go. So we've got gamma U minus 1 times MC squared. Okay, divided by Q is going to be equal to this potential difference that we need to fall through. So gamma U was 1.5, so this is 0.5 times mass times C squared divided by Q. What is Q going to be equal to? Why?
So, fuck.
Because it's a proton. It has one elementary charge. So the charge is going to be elementary charge 1.6 times 10 to the minus 19. Okay.
Sort of.
And it is, if his electron would have been negative, or would it?
No, it's still the same charge.
Okay.
We're just talking in terms of energy and the potential that we need to fall through. So you could put this in as negative if you want. Well, you could do that, and then you say a negative potential. In other words, the energy that the electron would have to climb. But it doesn't matter. It's just whatever way you think about it. We know the electron has to go the opposite way up the hill. Okay. So we get an answer here equal to 470 megavolts. Okay, huge freaking answer. All right, and if you can rotate ever so slightly. The last thing that I want to point out, and I'm glad that the book does this, although I think it might do it incorrectly. This needs to be checked. What if we did this classically? Same thing, and I said this is the amount of energy that we're going to get up to. And I want to know instead what energy we have to go through to do this from a classical point of view. In other words, our equation is 1/2 mass of the proton times the velocity squared is equal to change in V times Q. We still solve this. What was our U that we had before?
Oh, the 0.745.
Yeah, 0.745 C. That's the speed that we got up to. So if we solve this for this, we're going to find that we've got mass of the proton times 0.745 C quantity squared, all divided by Q, 2Q as it were, is equal to our change in potential. Now our change in potential here is going to work out to, I get an answer of 261 megavolts. The book talks about 291. I'm curious if they're actually dyslexic. You can feel free to run this calculation, or we can just not care.
That's a better option.
What'd you say?
So that's a better option. I was gonna do it, and I was like, yeah, I don't care.
All right. So the last thing to note as I'm handing this out is this chapter talks about particle accelerators. Now there's 2 different types of particle accelerators. Well, actually, there's a lot of different types.
You discussed these about, didn't you?
What'd you say?
You discussed these in calculus too, didn't you?
Yeah, I talked about particle accelerators a lot because they're really cool. Actually, we talked about fusion devices, which aren't specifically particle accelerators. The first type is where you just have a flat surface and you speed something up and you smack into it. Now, you have something that's holding it. Now, the problem with that is that in that you have initial momentum of 0 or no. Let me just talk. It'll be faster. No, your initial momentum is not zero because you have one thing that's zero and something that's coming in like this. So the problem with that is that the two constituents are going to move off. All of the energy of the collision is not inelastic, okay, because one thing was standing still in the first place. So if that's the case, then you haven't converted all that energy to mass. And this is the whole point of particle accelerators, is to try and figure this out. Instead, if you do things like CERN does, is you got two things that are rotating in the opposite direction like this and then smack them into each other. In theory, you can have a perfectly inelastic collision where you've converted everything or as much as you possibly can into pure mass. The whole point being is that we're looking for other fundamental particles other than the electron. Turns out that theoretically we think that they're going to be massive, much more massive than the electron, much more massive than anything that actually exists because we think that they decay very quickly. They do decay very quickly. That's why it's so hard to find Higgs boson. So we speed these things up, smack them into each other with all this energy, all of a sudden we create very massive particles that stick around for fractions of a second in the sphere.
I know somebody pointed out things.
We did.
Okay, so that
part's up.
Okay.
We got that.
I wasn't sure if that was like still in purity.
No, we've got that now. It was slightly anticlimactic, only because we've been spending all the time assuming that we would find it. So all of the papers and everything that's been written have all been assuming the Higgs boson will eventually be found. So it's not like this new breakthrough. It's like, oh, now we can do more. No, now we can just change this line that says assuming, says, okay, now we do Higgs boson. But anyways,
Is there any more frontier theoretical?
But I missed the goal.
tons.
So 30 points of that test.
And actually, the person who talked about that would probably be our Simmons.
My version
Simmons is particle
Oh my
physics.
God.
He's actually a quantum biologist. Okay, see you guys on Tuesday. Oh, and sorry, your graded work, I left it at home accidentally. So you get that.
It's just a nice.
He said that.
If you have any trouble with the rest of that derivation, just email me, let me know. You can show me where you're at, and I might be able to point you in the right direction. You can always just send me a picture with your phone.
You won't wait first as much.
Your new iPhone. Has anybody seen your iPhone tomorrow?
What?
That would involve getting an
Yep. You think I have to stick out of the phone at me right now? I got a 5S. I'm happy.
There you go.
I mean, I have 3. You know,
I just get the know.
You got a 4? iPhone 4?
I'm on for it.
do it.
Free upgrade. So.
I actually did better the first one I did than the rest of them.
Well, I think the biggest difference is
Yeah, but you know what?
you're a professor.
Well,
paid.
I said that.